Okay, today we are going to talk about a couple of things. We'll see if we can get through it all today. First, I'm going to start off with a couple questions people had about the homework. I guess in terms of general topics on the homework, then also problems people in general seem to be having a harder time with, and hopefully clear up a couple of maybe possible misconceptions. The meat of the lecture today is going to be first off we're going to continue this unit on, or this set of slides on evaluating machine learning algorithms. So these as a whole are about, we have these machine learning algorithms that we have been using so far. How do we know if they're performing well or not? And if they are performing well, how do we actually go about reporting that they're performing well on a paper, in a paper or something like that? So we're going to talk about cross-validation first. And cross-validation is really getting at the question of how we optimize things like the hyperparameters, like the lambda parameter here that I showed, like the number of basis functions, the bandwidth of the Gaussian kernel, these kind of things. Then we'll talk about a slightly different topic, which is very related, but it's a little different. And this is really about reporting the errors. How do we quantify the error and how confident we are in those errors when we're reporting our results in a paper or something like that? And finally, if I have time, I wanted to actually go through an example presentation. This is actually a paper that I had 2 years ago now on using a lot of machine learning techniques to predict home energy bills. And I'm doing it not because I think that this paper is particularly, groundbreaking in the field or anything. It's mainly just an example of using the stuff we've already learned, for the most part, to put together, a reasonable publication that actually that's been picked up by the energy and the machine learning community to a certain degree. And so, really, what you've learned already is you can use to do publishable kind of work. And so this is just sort of an example of one paper that uses these techniques to do some kind of interesting analysis of energy data. First off, though, let's talk about the homework. So one question people are having some trouble with is question 3. And question 3 is the one where I ask you to put various optimization problems in standard form. Right, so the question, I believe, is for the deadband loss. So we're saying we have this problem, minimize over theta, sum from I equals 1 to m of the max of 0 and this absolute value, or like this, theta transpose phi xi minus yi minus epsilon, like that, right? And then in the later question, I also say, okay, now we're also going to add regularization and penalize this. And in both these cases, I say to either put it in, I ask to put it in a standard form, which means I say either as an LP or as a QP, quadratic program, when you have this term. And what I mean by that is, remember, a standard form LP, for example, is the following problem. It's minimize over, all right, z, C transpose z, subject to A times x is less than or equal to, A times z here, is less than or equal to B. So in order to write a problem like this in standard form, what that involves is you have to specify what all these matrices and vectors are. So remember, in the case of class, this was the case for the absolute loss. We wrote it as a linear program by saying what these things were. So we would say, C equal, or rather Z is going to equal, first this theta vector that we have, and then these other new vectors. By the way, this is also the Greek symbol nu, not V, just as a FYI. The theta and new variables here are what Z is comprised of. Let me just fix that. The C term is equal to 0 here, because there's no thetas in the objective. And then, or rather, they're all sort of bundled into these new terms, because the new terms bounded the absolute loss. So C was this. A, I forget the exact signs here, but it was something like this, right? Negative I, then negative theta I, or something like this. maybe this was I and this was like that. And then it was B finally was equal to y and negative y. Something like this. I think this is right, but I think I'm probably missing, I might be messing up a sign in one of these two matrices. But it was something like this, right? So this was how we wrote down the absolute loss. That's not this one. That's just with this. You don't have the max or the epsilon there. This is how we wrote that absolute loss function in standard form. For a quadratic program, it's the exact same thing. You just also have one more matrix you have to specify, which is this P matrix. So a quadratic form says it's minimize this plus x transpose p x. And so you just have to fill out what p is here, too. Just tell me what that is. And in fact, if you want to, you're not required to do this for the homework. But if you want to, you can test whether you're right or not. And so at least you shouldn't, if you're not right, this should come as no surprise to you. The way you do this is we know how to solve these problems with YAML, right? It's pretty easy. To solve this, for example, you would write something like, you just write that thing, right? You write something like solve SDP. There's no constraints. And then something like the sum of the max of 0 and the absolute value of phi theta minus y, probably going off the screen there, minus epsilon, right? However many brackets you need there. This is all a parenthesis there. So you know how to solve this pretty easily with YAML, right? So you can solve that, and that will give you a solution for what theta is. If you want to, and if you have regularization here, you would just add this as well onto this objective in YAML. If you want to then look at the LP or QP formulation, well, MATLAB has functions. They're called linprog and quadprog. Linprog, I know. Actually, let me maybe check really quickly what quadprog's syntax is. But linprog, to solve that problem I had before, you would do something like linprog, z equals linprog c a b, where c is the objective term, a is the matrix of inequalities, and b is the right-hand side there. So that would give you the solution for this. Similarly, quadprog is the same thing. I believe it just has the P matrix first. They might actually scale the P matrix by 1/2 to check that. Type help quadprog to sort of see what the actual thing is, but it's just this. It's just going to be this. If you type that in, you'll get the solution to what z is. So what you can do, if you want to, and this is not required for the homework if you're sure that you're right, but if you're not sure, check it out and see. Type in your P, your C, your A, and your B. See what your result is. Theta is part of that result, right? Because like theta and nu or something like that's going to be your variable. And see if you get the same results as you do with this one. Then you know you're right or not. This is a very concrete problem here. There's no sort of, there's no sense in which this is sort of an abstract math problem. This is a very concrete problem. And if you can type it into MATLAB and you get the right solution, then you know you're right. If you don't get the right solution, or it's saying it's complaining or something like that, then you're not right. So you don't have to do this. You can just trust your instinct or be pretty sure that you got it. But you can always test these things. And that goes with the kernel one too, by the way. The kernel one's a little bit tricky because, especially for large, and I guess I'm not defining what phi is here. I'm just saying for anything. So you can just make up whatever phi and y you want. It'll give you doesn't matter what they are. This should give you the same solution as this one. For the kernel version, depending on how big you choose and sort of what you choose for k, you actually could come up with some numerical issues when you solve it with YAML, so be careful for that. But you can do the same thing in the kernel version too. The only caveat is be careful what you choose for your k matrix. So you don't have to do this because it can kind of be tricky at that point. Running these difficulties of sort of conditioning of the kernel matrix, but you can test in theory, and depending on what you choose k, it actually could work out fine. And so you could again test to make sure that you're getting the right solution to your problem. Okay? Yeah?
The kernelized one part, see, it's kernelized and you mean regularized, right?
Right, yeah. So whenever you use kernels, you should also regularize. So that, yeah, that is important. So yes, include the regularization term in the kernel version as well. So there's also this one on the kernel version. Let's close the door there. It's getting a bit loud. All right, so that was the first point. The second point someone asked about was, actually this is a more conceptual point, but what is bad about kernels? Right? Why wouldn't you just always use kernels? Other than, I guess, they might be a little more conceptually difficult. Why would you ever use features if it's just more expensive to always build them? So does anyone actually have an idea about, so we have least squares, right? Say we want to do this. We want to minimize over theta, sum from I equals 1 to m of, well, I just write it like this. Theta transpose phi xi minus yi squared, which just equals big phi theta minus y, 2 norm squared. So we can write this as instead minimize, maybe I'll add the regularization here. Minimize over alpha of this thing. It was k alpha minus y plus lambda alpha transpose k alpha. We can write it like this instead, and for the proper features, you can write it the same way. So like for polynomial features, you could use a polynomial kernel, or you could construct them explicitly for sometimes more effort here. But can anyone guess why you might want, so it sounds like this is kind of the right thing to do, right? It's sort of a better idea, because you don't have to compute them explicitly. Does anyone imagine why this might be better sometimes? Also, I'll just go ahead and write the solutions too. So the solutions are theta star equals phi transpose phi. Well, I shouldn't write this one because it's actually part of your homework. Let's leave this one out here. Phi transpose phi. The solution would be phi transpose phi inverse times phi transpose y. And this one would be alpha star equals k plus alpha I inverse times y. Sorry, lambda y. So why might, let's say you have a one-dimensional input, and you have, polynomials of some small degree, 3 or 4 degree polynomials. Can anyone guess why you might want to use, this sort of gets at question 4 a little bit, but can anyone think of why you might want to use this method? Yeah.
Seems like if you map these explicitly,
yeah,
all you really have to hold on to at the end is a vector parameters, where it does take more computation to get there. Whereas with the kernel, you're holding on just to the original data.
Yeah.
And it's not as computationally intensive to get to the parameters.
So that's a great point. The one caveat I would add is that not computationally intensive, that actually cannot be the case always. So it has to do with the size of these things, right? So absolutely, the point he made was absolutely right. So kernel methods, as I mentioned on the slide, they're what's called a non-parametric method. This means that you have to keep around your whole data to make a new prediction, right? Because anytime you want to make a new prediction, you want to predict on some new example, you have to sum from I equals 1 to m of all these alpha i's times the kernel function between the ith example and your new example. That means in order to compute this function, you have to keep these guys around, hold on to them, so that you can recompute those kernel functions when they come up again. That's potentially a big problem, right? If you have a lot of examples, you have to keep them all around. I would even, though, argue with the computationally more efficient part. So what is the complexity of doing this? How big are all these matrices here? So let's say that, let me make some concrete numbers. So let's say that n equals 1. We have a one-dimensional input. Okay? Let's say that k here equals 4. So we're going to use polynomials of the 0, so there's constant term 1, 2, and 3. So we have really degree of the polynomial equals 3. Okay, and let's say that we have 100 examples. What is the complexity of, well, first of all, how much time does it take to generate a feature vector? Let's see, how much time does it take to generate this guy? Phi. How big is it, first of all? What's the size of phi?
K by n, or m by k.
M by k, right. Phi is always m by k, no matter what. Doesn't matter what degree, actually, it is. It's just always m by k. So how long does it take to generate? This is sort of a trick question. I mean, this is not a trick question. It's obvious how much time it takes to actually, m by k. That's always the case. How much time does it take to generate this matrix? How much work do you need to do?
Was it the n plus d choose d with that formula?
But n plus d here, choose d, is what? Degree 3, 1. What is this?
Degree 4.
Yeah. That's not too bad. In fact, that is k. This is the definition. K equals this. That's the size of k. So, okay, so how long does it take to generate this matrix? Just rough estimate here. How much computation does it take to generate this matrix? Equals, so big O of what, I guess? How big is it?
M
By.
k.
So how many things do you need to compute?
M by k.
M what k? Not m to the k, no. Yes, m times k. Okay. How big is k? Big K. How big?
M by m.
Yeah, always m by m. So how long does it take to compute this one? Right, m squared. Which one's bigger? Right. So this is much bigger. Now, how about these? Do people know this? How long does it take to invert a matrix that's n by n? The computational time of that? Does anyone know? So if you have the matrix A that's n by n, does anyone know how long it takes to compute A? Well, that's a bad way of writing it. How long does it take to compute A inverse? Has someone seen this before? So the time it takes to compute the inverse of a matrix? Approximately? Okay. It's n cubed. Convenience is order n cubed. Storing it, you have n by times n elements. And to invert it is n cubed. Essentially what you do is like when you solve a set of linear equations, you add things to each other to cancel out certain terms. You multiply rows by other rows to cancel out certain terms. You do this until you have only one variable left, and then you solve, substitute it back in the thing and solve the rest of them. That first step of multiplying everything by each other to cancel out takes time n cubed. It's actually really good n cubed. It's like 2/3 n cubed is the actual constant for a general matrix, and for a symmetric matrix, it's 1/3 n cubed. So it's really low constant term on that order there, but it's n cubed. Okay, so how long does this take to compute then? What's the running time of computing theta? How big is this matrix here that we're inverting? This whole thing. What is it? Yeah, it's k by k. So what's the running time for this whole thing then? So we said something. What? So yell it out. What the terms are? Yeah. So there's a k cubed. Now what's the other one? This one's actually a little tricky. But if anyone has any guesses, how long does it take to form that matrix? K squared times, because right, this matrix is what this matrix is this is every element here is the inner product of all the examples times all the other examples, and you have to do that k squared times. So does anyone have a guess about the order of computing this guy? So actually, let's just write it term by term, maybe. So here, let's see, theta transpose times theta. What's the first element of this equal to? I'll write theta now. Apologies for this. I'm going to write it by columns. And this is not theta of x1. This is theta 1 for all the examples. Okay, so the first element here is, actually, does anyone, what would this first element of this guy be? Yeah, it's going to be theta 1 transpose theta 1. Right? And you have to compute. And so how long does this take to compute? This is, remember, m by k, sorry. How long does this inner product take to compute? First of all, how big is theta 1 here? What's the size of this vector? M, right? So an inner product of two m vectors takes how long? No, it's an inner product. Right, it's order m. I mean, you're just taking each element, you're multiplying by itself and doing that. So every element of this matrix takes time m to compute. Does that make sense? Why that's the case? And there are k squared of them, because this is a k by k matrix. So the term here is actually mk squared. Usually, I mean, either of these could be bigger, but usually this will be bigger. Sometimes, actually, well, not always. They can both be big, depending on if a or k or m is bigger. Okay. What about this one? How long does it take to form this guy? K. We said it already. What was it? To form, sorry, someone said it? To form K? We went through that before, just now. Yeah, K is m squared, because it's just m by m. I mean, technically, it depends how long it takes to compute each element of K, but I'll just give you, the complete benefit of the doubt here and say we can compute each element in constant time. That's sort of the kernel trick, right? It's each element's really fast to compute. Normally, it has to compute this big inner product, but here it's just essentially, maybe order n or something like that, but n is really small. So we'll just say it's order m squared, but then how long does it take to actually invert that? Would it be then, if it's an m by m matrix? Right, so it would be m cubed. So if in this case, how big is this? To a constant term, what's m cubed there? Right, yeah, so like 1,000,000, right? Or 100,000, no, 1,000,000. Yeah. How big is this one? 101. Well, maybe it's not saying also. So, yeah. So approximately, right? Yeah. I mean, 1,600 plus whatever, 64. Right. So the time it would take to do this is just for 100 examples. There's not a lot of examples. The time it takes to do this is huge compared to this. When you have a small number of features and when you have a even reasonably sized number of data points. But even more sort of what you can obviously see is that when m is greater than k, this will be bigger than that. When they're equal, they're about equal. I mean, that's just fine. And when k is much bigger, that's the case I was talking about, right? When essentially n and d are both really big, so k is huge. That's the number of features is huge. This is the one case where the kernels really make a lot of sense, and m is sort of small, reasonable size. Then doing anything in k squared is hard, let alone k cubed. Even storing k memory-wise is hard. So that's the regime where you really want to use kernels. So hopefully this sort of gets at some of the questions in part 4, because this sort of gets at when do you want to use one method versus the other one. Okay. Is everyone with me on this? Because this is sort of an important point, and both from a sort of intuitive standpoint of why these things are hard to compute at different times, it's good to know, when you want to use this versus the other one. It's really important to know. Yeah.
So can you just say that one time? So when m is greater than k.
Yes. So remember what these are too. M is the number of examples. M is always the number of data points you have. K is always the number of features you have. Right? So these are the two orders there. So from that, it should be obvious when you would want to use one versus the other. And also importantly, don't confuse k and n here. K is the number of features, n is the dimensionality of the input. The number of features you use will depend on the dimensionality of the input and the degree polynomial you have, or the number of RBF centers you have if you want to cover the space entirely. These things are related, but they're not the same thing. Okay? Okay. Let's then move to this discussion of evaluating machine learning methods. Are there any more questions about this? We're having office hours tomorrow, remember, 2 to 3. So come by. Everyone should have at least started the homework by now. The other thing is, I think the course, for whatever reason, everyone is enrolled in 884 right now. And if you know about the homework, I mean, this is meant to be the harder version of the two. So if you find yourself beating your head against the wall with the harder things, come talk to me, because really maybe 484 is the right thing to be in. If there are logistic issues, like you need grad credit or you're a master's student and some things don't count for credit or whatever, come talk to me about that too. I mean, I can work out that stuff, but that shouldn't be what constrains you. What makes you take one versus the other. And you can switch now, by the way, too. Even though it's after the deadline, you can, it's easy, I've just done in the past, switch people from one to the other because it's the same course, you've been coming to it. So it's easy to switch, but really genuinely kind of try to evaluate. I mean, 484 is still very hard. There's a lot. I mean, even those problems before the 884 only problems are tough. So as I said, the homework should take you between 15 and 20 hours to do. If it's taking you a lot more than that and you have not started the 884 problems yet, then come talk to me, because you're probably not in the right. I guess because that's for everyone, because everyone apparently has ended up in 884. So, you know, if it's just a matter of credit, come talk to me and we can work that out. If it's, but you know, pick the right one based on the homework and the level of difficulty and sort of the background you have. Okay. So after saying that, let's jump back in. All right. So what I was talking about last time was this notion of training error versus testing error, right? And the notion here is that if you train on a distribution and just evaluate, sorry, not a distribution, a set of data. So if you train on a set of data and you do things like add a feature to your representation, when you now minimize your loss function, you will be guaranteed to achieve a lower loss than you did if you didn't have that feature in, right? Because you can only do better. You can't. I mean, you can do the same. The feature is really useless on that data. But if you could only do better if the feature is in fact somehow correlated with the output just on the examples you've seen so far. But that isn't really what's important to you. What's important to you is how well it performs on a new set of similar data. Right? And this is why we separated out training sets and testing sets. The training set was going to be the data that we fit the parameters to. Right? So training is you pick your parameters theta to minimize. It's the argmin. It's the minimizer. I guess theta star equals the minimizer of your loss function on the training set. L of theta transpose phi xi, and then yi. Okay? Then testing, or evaluation, is that we had some other data set, and we want to say that the error equals the sum from I equals 1 to m of this same loss, but evaluated on different data points. And sorry, it was m prime here. I have m prime testing examples and m training examples. So the sum from I equals 1 to m prime of the loss of theta transpose phi x prime I and yi prime. Right? So we're still evaluating using this loss function. We're not changing losses when we train versus test. It's just that we test on a different set of examples than we train on. Okay? So what I'm showing in these graphs is the training error, which is just the or I guess I won't use the term error. I'll use terms something like average squared loss, or the average loss. For, in this case, different values of lambda, I'm showing the training loss, the loss in the training set, and the loss in the testing set. And this kind of cartoon here, well, this is actual real data, but this kind of figure is exactly sort of the picture you should have in mind about what this looks like. So I guess sometimes it's kind of the reverse of this, depending on whether raising or lowering something makes the model more complex or not. The picture you should have in mind is that you have, let's say, your training error, training loss like this. Your testing loss is these dots. And so this is, I guess, this average loss on the y-axis, and then some notion of the complexity, model complexity, on the x-axis. So this would be, for example, if you're adding more features, then the more features you add, the more complex your model is, the more power your model has to represent things. If you're talking about lambda, the regularization parameter, then actually bigger values of lambda would be lower complexity models because you're restricting the weights, essentially. You're making the weights smaller, so those models are less complex. Whereas if you lower lambda, you will have more complex models. Okay, so this is just now the notion of model complexity. And what happens in training loss is that it starts off, with a simple model and you suffer this amount of loss. It wouldn't be infinite here, by the way, because even if you predict 0 for everything, that's kind of the simplest possible model, right? You will still get some loss. I mean, this is not an infinite amount. I guess it could be for some loss functions, but usually they're not infinite like that. You will still suffer some loss. So you'll have some finite amount here with a model of very low complexity. You get some loss. And then as you increase the complexity of the model, your loss will go down. And eventually it actually will probably, depending on, I guess, the class of function you're talking about, it will maybe eventually hit 0. For lambda, it wouldn't, right? Because for lambda, the most complex model you could have is where you're not penalizing at all. That's just the normal, say, least squares model. So it wouldn't hit 0. But if you're adding more features, as we talked about before, you add enough features, you will get 0 loss on your training set. Right? So this goes down and will always keep going down as you make a more complex model. And it will never go back up. What testing loss looks like is that, and I'll draw it separate, it can actually really overlap with training loss at the beginning. It really should, in fact, overlap with training loss at the beginning. But what happens here is that as you start increasing your model complexity, I mean, at first it's probably the same point because you're predicting 0 in both cases. They're, by definition, as long as these data sets are similar, you should get similar average loss on them. What testing loss will do is it will, in the same way, kind of come down for a while. But then at some point, your model starts overfitting to your data set, right? You start sort of fitting the idiosyncrasies, the noise in that data. And this is that high degree polynomial that passes through every single point without really capturing the underlying structure. So at some point, your testing loss will start going back up. And as you might imagine, you probably want to pick the point that's right around there. So we'll get to that in a second, how you actually do that. So OK, here's kind of the cartoon to have in mind. Every one of the pictures I'm showing you is an instantiation of that cartoon. OK, so here you have lambda's kind of a nice one because lambda is usually kind of the performance is somewhat smooth in lambda. So this is a fitting that our typical example of the predicting peak demand from high temperature with, in this case, 70 radial basis functions. If you don't regularize here, it severely overfits, so that's not what you want to do. But what you see there is this thing just with the x-axis flipped, because this model here is where you have high lambda, that's heavily regularized, that's a very low complexity model. And here you have lambda equals 0 essentially, so you're not penalizing, so that's a high complexity model. So complexity is really increasing this way. And this is the cartoon you see. Don't worry about the absolute levels of this. Sometimes this one comes up to a fixed length is better than that, sometimes it's worse than that. It can be either one. What we saw in the previous 2 slides was the opposite of this thing. So here what you saw was that here when you have the number of radial basis functions being your thing we're varying here, complexity is increasing this way, right? Because the more basis functions you have, the more complex your model is. And so this is exactly the behavior you see again. There are some little jumps here, by the way. Those jumps can happen. It's not perfect like this. Maybe actually let me zoom into this. This is what you see for 2 to 12 or so. Loss starts up high, it comes down. Training loss just keeps going down and down. But testing loss, which is the green line here, will go back up. Again, it does weird things, the idiosyncrasies of the data, but it goes up. I'm actually also plotting this on a log scale, notice. So this is actually really high loss. I mean, look, this is the scale of loss on the first for the small amount, and all of a sudden you have loss on the order of 10 or 100. I think polynomials are the same thing. So polynomials actually get 10 to the 2. So these are really, really bad, this loss here. we have, a logarithmic scale here. So you wouldn't even be able to visualize what it looked like in the, if I plotted it with a normal axis on the y-axis, it would just look like a line. You wouldn't even see that first bit down here. So this is the cartoon, and these are instantiations of this cartoon in all three cases. So now we come to a point of how do you pick then how complex a model you should use? And so the standard idea is, well, I shouldn't say it's a mistake. Maybe I should just say what I do first, and you can tell me where the mistake is. So here's what people do then. So, okay, I have my data set. I'm not gonna test and report errors on, or I'm not gonna choose my parameters. I should actually also mention, I may have said this word a couple times now, but theta I'll always call parameters, and other things that are variables like lambda, like the bandwidth of the kernel, like the number of bases you use, those are all called hyperparameters. So just as a term, the things that dictate kind of the overall number of bases, the complexity of those things, those are called hyperparameters. And theta is the only parameter. That's just notation though. Don't just know what I mean when I say that. So to pick my hyperparameters, that means picking lambda, picking the dimensionality of the kernel, picking the bandwidth of the Gaussian kernel, all these things. To pick them, what people will do is they say, okay, I know not to pick them based on the training set. That's a bad idea. So what I'll do is I'll split up my data into testing and training sets. I'll do it like this even. So I'll use the thing we did before where I have all my data here. I'll randomize the order, then I'll split it 70-30, because that's what everyone just happens to use for no good reason. And 30% becomes testing, and 70% becomes training. All right, then what I do is I run this plot. All right, so I try a bunch of different parameters for lambda. I say, hey, look, in this range, this is good here. This is where I want to be. So I pick lambda equals, say, 10 to the negative 2 or something like that. And then I go ahead and say, okay, I'm going to report my error to be whatever this is here, this value, whatever that may be. Let me go back here. So for example, picking my number of basis function, or RBFs rather, I would say, okay, 8 looks pretty good. I'm going to pick 8. Maybe 4 actually, because there's a few less that doesn't appear to help that much. So I'm going to pick 4 real basis functions, and my error is 0.28. And that's the number I published in the paper. Can anyone say what's wrong with that? Yeah?
Will it sense you're now just overfitting to your testing data?
Yeah, exactly. Does everyone understand what's going on here? So I'm cheating, right? Because I'm picking, they're still parameters of my overall system, and I'm picking them to get good testing set performance. Just the way I picked theta to get good training set performance. So if I have enough hyperparameters, just like with theta, if I have enough different ways of regularizing or enough different sets of features I can pick, well, I'm just going to do really well on this. I'm just going to pick exactly what gives me the best performance here. With theta, determined by this, but basically I'm going to pick the best mapping that, when I choose theta based on this, gives me the best performance here. And I'm using my test set effectively as a training set to train my hyperparameters, and then I'm reporting this error, so I'm really reporting, in some sense, a kind of training error. Okay? So you can't do this. So this is the common mistake. Common mistake is to pick the parameters based on the testing set and report these results. Or use these best features and whatever. What you want to do instead is a technique called cross-validation. So what cross-validation says is, let's take this one step further. We know, okay, I guess this is what I was saying before. We know that there's still something kind of right about this method, right, where we're picking hyperparameters based on some other set that isn't part of our training set. But we can't use our test set as that other set. What we do instead then is we take our training data, the remaining 70%, and we split it again. say 30, doesn't matter. I'll call this like 20% or so. And I'll call this what's called the cross-validation set. So we split our remaining training set into a training set, a real training set, for real training, and then the rest a cross-validation set. And that is the procedure you actually want to do. You pick your hyperparameters based on this plot where the green line is evaluated on the cross-validation set, not on the test set. And then, when it's all over with, you run it once on the test set just to report that result. So here's the actual thing you should do. Here's the actual cross-validation procedure. So first of all, I break data into training testing, randomly, say 70-30. Then you break training set again into training cross-validation. Say you do 70-30 there, or whatever this is here. This is about 70-30, not quite. Then you choose hyperparameters using the cross-validation set. Your parameters theta are always trained from the training set, from this training set here. But you choose your hyperparameters, your number of features, the degree of your polynomials, et cetera. You choose those based on performance on the cross-validation set. Then this stuff is optional, but it's probably a good idea. And sometimes you don't want to throw away data, right? And if you do this and then just use this model, you're not really fitting the data, your parameters using this model. So you pick the hyperparameters based on the cross-validation set, but then you retrain your model using all this data, because you might as well use it all. But that procedure is optional. And for big enough data, maybe it doesn't even matter. You don't even have to train it anymore. And then, finally, you do this once, and you do it only once, hypothetically, right? You train your testing set, and you report that error. And you only do this once, right? Right before the paper's due, you're sure, because you're so confident in your methodology that you just know you're not overfitting your cross-validation set, and you're just going to evaluate once. If the results are bad, then you just shelve the paper and never look at it again, because the results were proven wrong by statistical measures. This is what everyone is supposed to do, and it's also the biggest one of the biggest sources of potential bias and error. I'm using those terms kind of in their informal meaning in a lot of applied machine learning work, because of course no one actually does this, right? What you'll of course do is you'll do everything like this still, but then you'll evaluate on the test set a couple times, and you'll say, oh, well, this doesn't look that good. How can I change my algorithm to make it look better? And you'll change your algorithm a little bit, and then it'll look a little better. And that is, in effect, overfitting to your testing set, right? You actually are overfitting to your testing. You're doing the exact same thing. You're doing human hyperparameter tuning, or meta-level tuning based on this testing set. This, for example, some of the relevant critiques of, for example, climate models would be to say, they aren't doing this, right? They are, and I'm not using any terms here, because this is not like I'm not making this claim, and I definitely have a very large faith in these things. But some of the more legitimate claims, and you can make legitimate claims about kind of the margins here, would be to say, well, look, you've built your models so that they fit what we've actually seen in the real world. We don't have an independent testing set we can actually evaluate these things on. So you've overfit to what's happened before. And so if you've seen any kind of warming due to CO2 release or any other factors, it's we can't know from these models that it's really due to the CO2 or due to human effects. This is maybe a bad example, because I don't think that's what's actually happening in the climate models, but it's important to understand that these things can be valid critiques too. They're usually not put up, actually given that way a lot of times, but it's very legitimate to critique the scientific or the statistical validity of a lot of models if you worry that the person building the model spent far too much time kind of getting lucky in their test set, or doing kind of meta-level optimization while checking results from the test set. I think there was recently some big paper that claimed like Twitter could predict the stock market, what it was going to do in a few days. That has had maybe it's been validated since then, but I know immediately afterwards there was a lot of critiques on this, basically saying you just tried enough stuff and so you got something that worked on your test set. These are not actually valid results here. So this happens in practice, is my point. And you should not use this as a blanket to critique every single piece of work, but just know this. And in your own work, you're going to do some of this. It's just human nature. You're not going to close your eyes to the test set, have no idea what you did on it, and then the day when the paper gets submitted or not, or trashed forever, evaluate the test set. Yeah.
And before you trash the paper, could you try to just reshuffle the data between these 3 sets and do your evaluation?
Just reshuffle the data until it looks good? Is that the idea?
It looks good, but to let you experiment again without having a bias?
Right. So certainly, one thing you can do is do this same thing multiple times with different random sets. And get multiple estimates. When you do that, there are very specific rules as to how you are supposed to combine these things. You can make assumptions like these things are all independent. These different random folds are independent, and therefore I should be able to do this, and they're all independent. But of course, they're not independent because you have some overlap of the data. It's the same data. If you have data where you could just grab as much as you want for free of different data, like from the web or something like that, you could certainly grab a data set of size 1,000 of web pages and then grab 1,000 more web pages and do that. Then you can actually just average your test errors in certain ways and actually get confidence bounds on where that test error actually lies. So we'll talk about that next a little bit. Not quite to that extent, because we're not going to talk about the multiple randomization procedure for doing this, but you can do it, and there are correct rules for that. A lot of these things, the correct rules, you have to talk with a statistician to find them out, because I even forget sometimes what the correct, kind of tests are for all these different cases. But yes, there definitely are things you can do to get better estimates with a fixed amount of data, but you have to be careful. A lot of things that you would think give you better estimates actually statistically do not give you better estimates. They just are really reinforcing the same thing over and over again. So they are actually very dependent, and so they're not giving you it's not like they're giving you independent samples. Don't worry about that, by the way. I'm just putting it out there to say that there are things you can do. I'm not saying what they are, but also I'm saying be careful, because some of the obvious things do not actually give you more information than just one single evaluation would. Is sort of a general statement, but we'll shelve that for now. Was there another question? I thought I saw another question. No? Okay. So bottom line is be careful when you do this, because you probably will at some point overfit to your testing set, whether you want to or not. Actually, has anyone heard of this online, I'm kind of rambling here, but has anyone heard of this online competition, machine learning competition webpage called Kaggle? So actually I know some of my students have, because we're actually doing some stuff with it, but it's a machine learning competition website. And what they do is they give you a training set, and you run your machine learning algorithms on it, and you then submit results. And they also give you a testing set without the answers. And you submit results in the testing set. And then what the results you submit are actually on the testing set and a separate final testing set that they have. And so you get results back on the sort of first pass testing set. You get the results. And then the final results for the competition at the very end are computed based on this sort of last testing set. And a huge amount of time in these contests, the people that are on the top of the leaderboard based on this first testing set are not the ones at the top based on the second testing set. So basically, they are overfitting to this testing set. Even though this should not be possible with a good, well-designed problem, it happens all the time in practice. So people overfit. You make decisions that bias you towards one type of algorithm based on the fact that even if you don't really know all the true ground truth, you just get one number back saying 90%. Even that will cause people to overfit to data sets. It's unavoidable, unless the problem's really well designed. If the problem is even slightly poorly designed, it's really easy for this to happen. So be cautious about this, would be my only comment. Yeah?
So just returning to the cross-validation, so if you view it as basically you're trying to estimate your true testing error,
yeah.
As you decrease the size of your cross-validation set, your bias will go down, your variance will go up. So if you view cross-validation error as like an estimator of your kind of final,
right,
So I guess what I'm saying is the upshot of what I'm saying is as you decrease or increase the size of your cross-validation set, you could be introducing different sources of errors.
It should be an unbiased estimator of this. I mean, it should be.
I guess relative to actually step 4, when you're training on the entire.
I see. So what that comes down to is data size. So as you add, right. So because this is less data than all of this, you actually might not be, this ideally could actually be better than all of this, right? Because this could actually, so there's a little bit of bias there. The thing I would say for that is that that's usually pretty minor, because that is usually going to be kind of basically it just means that as you get more data, you can use more complex models that have less bias, this kind of stuff. But that usually is a fairly minor effect on these things. Just because typically, 20% more data makes a difference. But if you're in that regime where that really makes a huge difference, just collect more data if you can. I mean, don't waste your time on this kind of stuff. You can also do things like, I don't know if I mentioned this, but things like leave one out cross-validation, where you actually treat every single, actually you can do a few things. One common thing to do is something called k-fold cross-validation. This is where you divide the data set up into k different folds. You train on all but one and test on the remaining one. So maybe I'm going to say it this way. One problem with this, right, is that you're still kind of at the whim of whatever random data you picked in the different sets. This gets back to your randomization issue. So you could do this instead. This is a common thing to do instead for cross-validation. You can do it for testing error too, but statistically, it's not necessarily that much better an estimator of the true error than this. It's actually really hard to show that cross-validation or k-fold cross-validation is a really good idea in practice. But what you do, don't pay attention to that. It's very good in practice, but theoretically, it's hard to show a lot of properties about it, k-fold cross-validation. So what you do is you divide your data set, your training set, your new one, up into k different folds. So we have 5 folds here. You train on these ones and then test on this one. And then you train on these 4 and test on this one. And you add up all your testing errors and use that as a thing as your average. So there, in that case, you've actually tested on every single example in your training set. So it's, in some sense, every single example in your training set is factoring in to your hyperparameter selection, those kind of stuff. So you can do that. And in fact, in the paper I'm going to talk about, I do that for the final testing set, a similar thing. But again, the tests there that you have to do to make that work are a little more complex than what I'm going to show you here.
Basically the crux of my question was how do you trade off kind of exactly what you're getting at, the number of folds versus the size of the folds, because that can basically. Maybe for 10-fold data, you're talking about a factor of 1.1 difference in the data size between training. So this would be 20% difference in this. If you have 10 folds, it's 10% difference. That hopefully will make a huge difference in your actual performance. So that much more data. If that much more data really helps, then just get that much more data and be done with that. And the extreme version then will be what's called leave one out cross-validations, where you have one example in each of these folds, and so you train on all the data but one example and test on the one remaining example. All these things here, other than what's in the slides, we're not gonna do any of that in the homework. We're not gonna evaluate on that, but it's just might be good to know, especially if you see these terms in papers or other sources. Okay. Okay, I even have it here. That's right. I forgot that I had this slide. This is where it was. So we have this k-fold cross-validation case and the leave one out cross-validation. Again, you won't be tested on this other than just maybe knowing what they are. Not going to be tested on anything really, but you won't even have homework on this, right? Okay, so let me talk about the last subject now, and hopefully we'll be able to get through this. And we won't do the paper, but I'll do that at the beginning of class next time. So the question now is, if we want to report the performance, how do we actually do this? And so we know the right way of doing that. We train however we want here, and we have tests. And we test on our testing set, and we get some error or some loss, and we report it. We say, we have 90% error. That would be actually, for classification, say 0, 1 loss. Or our mean squared error, our average squared loss is
0.1. And the obvious question is, well, okay, is that good or is that not good? How does it compare to a very simple baseline? And how confident are you, by the way, in that? If you have one example in your testing set, say for classification, and you get it right, you could say you have 100% accuracy, right? But it's probably not something you're particularly confident in, right? So how do you report not just the what you've done, but also some measure of confidence in what you're reporting? And here we'll talk about two things that we actually might want to, actually maybe I'll go wait to the next slide of that. But the two questions I sort of want to address here is, if we have a training set of size, a testing set rather, with 1,000 examples, shouldn't that somehow imply that we're more confident in our result than if we have a training set of size 10? I mean, you would think it would, right? But shouldn't it? And what about the actual predictions themselves? Is it the case that we're getting a lot of these exactly right? So say we're looking at squared loss. Are we getting a lot of them exactly right, and we just have a few that we're getting very, very wrong? Or are we getting them all kind of within a reasonable range? What does the distribution of our errors actually look like? And these are two different questions here, and it's important to know these, to understand these as two different questions. So again, our setting here is that we have our testing set, right? So that's going to have our inputs xi prime and our outputs yi prime. Xi is going to be in Rn. We won't care about this. It's just the inputs. Outputs here we'll talk about regressions, so they're in R. And we have m prime of these, right? We also, for all of these outputs, have our predictions, y hat I. I should mention, in the typical case we're talking about here, for the testing set, we will still have labels for that, right? Maybe I didn't make that clear before, but the testing set, we do still have the ground truth for. It's just that we're not going to train the algorithm on that. So we need to evaluate the algorithm. If we don't have any labels, then it's very hard to evaluate the algorithm. So we have the ground truth, so test set. And we have our predictions in R. And now there are really two different things we can care about. The first one of these is, what does the distribution of our errors look like? If we just plot the actual error, not the loss, I'm talking about the actual just difference between our prediction and the actual label, or actual output. So if we look at y hat prime I minus y prime I, what do these look like? So this can be positive or negative, right? We can miss one way or miss the other way. What does the distribution of this look like? That's an important question, right? Because that will quantify, say, are we getting a lot of things, far away, and most of them really close, exactly right, and a couple far away? Or are we getting them all kind of in the same bandwidth? Those two scenarios could be the exact same average loss, right? We could have this sort of histogram here look like, this is going to be 0. We could have a bunch here, or we could have, a bunch here, and a couple over here, and a couple over here. These two scenarios would give the exact same loss. But they're very different in terms of the actual, what the algorithm is doing and how well it's performing. The second question, and this is a different question, is if we want to report some average loss, and that is, we evaluate the loss, for some loss function between y hat prime and oops, that should be y prime I and y prime hat I. A lot of little decorations on those y's at this point. If we want to report our average loss, this is that number we saw on those, or that graph that we saw. If we want to report it at some whatever value of the hyperparameters we picked, how confident are we in this value? If we have one example, we're probably, when we say, okay, we have loss 0.1, we probably aren't very confident. If we have 1,000 examples, shouldn't there be a way in which we're more confident in that? And I'm going to show only the most basic way of doing this. There are much better ways of talking about confidence in your predictions. But I'm going to show a very basic way, which is very basic, but honestly, this is what everyone in machine learning papers should do most of the time. So it's sort of fine to think about just the simple case. Okay, so let's talk about the first one. Before that, I want to just introduce some very basic probability notation because I kind of have to talk about this. This course is sort of machine learning without probability, which is an oxymoron to a lot of people. Right? I haven't talked about probability at all, really, in this course yet. Maybe very briefly in terms of like logistic regression, I mentioned it has a probabilistic interpretation, but I haven't really talked at all about probability. And that's actually probably okay, but you probably, if you go on to study machine learning in more depth, you're going to have to look at the probabilistic interpretations of everything. I've been talking about everything kind of in terms of optimization, but to talk about this part, we have to have some very basic probability. So we're going to use the capital letter Z to talk about a random variable. And don't worry about what these are formally. Just think of them as a quantity that can take on multiple values. With some probability, take some different values. And we'll use P of Z to denote its probability density or its distribution if it's discrete valued. The expected value of this thing is going to be the integral or the sum of the value of Z times the probability density of Z. Integrated over all of its domain. It really just means the average value it takes on is the expected value. The variance is the expectation of the value minus its mean. This is all we need to know. So now we're done. So actually, who here has seen basic probability like this before? OK, so most people, but if not, it's really no more yet to know, so don't worry. And by the way, if you don't know it, there are a bunch of good reviews available, and we're just using it kind of as a formula anyway. So suppose we have a bunch of samples that are drawn from some distribution D. What I mean by that is I have some distribution over my random variables, and I take a bunch of, so maybe this variable can take on the value 0 with probability 0.5 and the value 1 with probability 0.5. When I say I draw samples, I just mean I just draw instances of that. Each one has 0, 1, value 0, value 1, and the probability of being each one is 0, is 0.5. So I have a bunch of samples for distribution, but this is really very general. I mean, I can have, and you've probably all done this before, even if you haven't seen this formally. You've drawn stuff from a random normal distribution by typing rand n in MATLAB, or a uniform distribution by typing rand in MATLAB. So from these samples, though, and this is kind of the important point, from these samples, we can form empirical estimates. We can estimate what the variance and the mean are. And it's very intuitive how we do this, really. The mean is just the average value. So we add up all our samples and divide by the number of samples we've seen. That's this line here. That is an estimate of the sample mean. We can do the same for variance. For variance, we first compute the mean, and then we compute the average of our sample minus its mean. And again, we just divide by m. M is the number of samples here. You may have seen this variance estimate with an m minus 1 here instead of an m. What that is that is the case if you are in the setting where neither of these two things are known. Then using 1 over m minus 1 sort of inflates the variance a little bit because you're dividing by things that's a little bit bigger. What that is that's sort of a technical thing you need to make this what's called an unbiased estimate of the variance to make it's an expectation to be equal to the variance. But this is a different estimate of it. It's also an estimate of the variance. And in our case, we're going to talk about pretty big values of m, so we're not going to differentiate here. Just know that you might see both of those before in practice. OK, so you might see it with this. But basically, this is sort of the obvious form. The variance is the average, the expected value of the random variable minus its mean. So we just take the mean. Sorry, the variable minus its mean squared. So we take the variable, take its mean, and square it, and we take the average of those values. OK. So now, when I talk about looking at the distribution of errors, we can just plot that, first of all. So I drew these histograms here. We could just plot a histogram. Everyone knows what a histogram is, by the way? You just sort of look at where these things, what the value of this thing, and you sort of put them into buckets, and then the height of that bar is the number of things that fell into that bucket. So we can just kind of plot this and say, here's our error distribution. But we can also do things like plot report the mean and variance of that distribution. So we can treat these as samples from some distribution and report its mean or its variance. Now, these have different terms. So if we want to know about the mean of this thing, this is called sometimes the bias. It's essentially how far off are we from getting this right kind of on average, right? Because this thing can be negative or positive. If it's always positive, then you're kind of making predictions that are always too low or too high, depending on which way you write that. And so you could do better just by adding a constant to all your predictions, essentially. In fact, for the training set with something like least squares, what you can show is that this thing on the training set will always have 0 mean. Otherwise, right, you could just get a better thing by adding a constant, but we know we're doing the best we can, so we couldn't have that be the case. So as far as the training set goes, it can be non-zero mean on the test set. You could just have some weird thing in the training set that makes that bias in the test set. But because the predictions usually are reasonably close to 0 mean, it's oftentimes the case that we just kind of assume this is 0 mean even on the testing set. And so we just evaluate the variance of this distribution then. And you can form an estimate of the variance. This is exactly the squared error. So actually, one reason why people use squared error like this is that it is an estimate. It is trying to minimize an estimate of the variance. There are other estimates of the variance, and depending on the distribution, you actually want to use different estimates of the variance sometimes. But this is a reasonable estimate. For example, for Gaussian random variables, this is a very reasonable estimate. But it can be a reasonable estimate for any 0 mean value, or 0 mean random variable too. So in some sense, the mean squared error, this is the average squared error, which was one of our loss functions, right, is just trying to minimize. One way to interpret what least squares is doing is it is trying to minimize this estimate of the variance on our training set with the hope that it also is smaller than on the testing set. As long as you're in the regime where these two things are close. So that gets to sort of that first point. Basically, how do we quantify this distribution of errors? You can do it by just plotting a histogram. You can do it by talking about what the mean squared error is. As long as you understand what the mean squared error is that is the variance of that distribution of errors under this estimate of the variance. But now let's talk about a slightly more involved question. And that is, if we want to report some loss, what do we say about that loss? Can we sort of say how confident we are that loss, that if we had an infinitely sized testing set, how confident are we that the loss we report is the same as what we would get on that infinitely sized testing set? And here you do something a little bit different. So here I'm drawing something else. I'm actually plotting here a loss function, a histogram of loss functions. So whereas before, this thing here can be positive or negative, and it has no notion of a loss function, right? I mean, we sort of talked about maybe the squared error is an okay one because it has, this property of being an estimate of the variance, blah, blah, blah. But this in and of itself, this quantity is just a number, and it can be positive or negative or whatever. The losses, on the other hand, are always positive. Right? We know that because loss by definition is always positive. And they depend on what you actually pick here. So here I'm plotting a histogram of the absolute loss between the prediction and the actual output value. This is all going to be on this side. And if I take the average loss, what I am reporting is really the mean of this distribution. So I'm taking or an estimate of the mean of this distribution. Right? So I'm taking all these things. I am treating them as samples for this distribution, and I'm reporting its mean when I report the average loss. Okay, and this is subtly but importantly different from looking at the mean of this thing or the variance of this thing. Because now I'm just treating whatever loss function I have as the loss. It could be hinge loss, sorry, that's for classification. It could be absolute loss, it could be squared loss, it could be this epsilon insensitive loss, deadband loss, all these things are possible. And the question is, I'm now going to report that loss. How do I actually go about reporting it? Actually, how many slides do we have? You know what? I'll get to this last bit next time in class, and then I'll also finish up with the talk next time too. Importantly, one important note: it's kind of going to happen at a bad time because I'm just going to have started the power systems unit now, finish up machine learning. But next Thursday, we're not going to have class next Thursday. Going to be traveling, so can't make class unfortunately. The homework is still possible to turn in by then because you have late days, right? So if you turn in the homework after next Tuesday, just write down the time you're submitting it and slide it on the door to my office, or bring it to my assistant, who I will leave a note at my door or something like that about where to put it. But you can just shove it put it on the door too. It's fine. It's all covered in the honor code, so please write the actual time you hand it in. I think Sheila will probably come pick them up every day, so if you lie by a day, you probably will get caught. but just don't. Just write down the actual time you're handing it in. You have 5 late days, but really don't use them all right now. That would be a really bad idea. I'll just let you know. Please don't use them all because you will wish you had them later on in the course. So all right. Again, office hours again tomorrow from 2 to 3 tomorrow in the office, and then again on Monday at the normal time on Monday. But I will see you all soon.